everybody for joining this wonderful session. Hi, this is Tirtho with Harmanan, Michael, Aditya, and Shivansh, representing the topic TinyGPT-V efficient multimodal large language model via small backbones. In this slide, we'll discuss everything about TinyGPT-V, including next slide, please. Overview and related work, how the entire thing is built and what is the purpose of of this model. Then model architecture, how the model is built. Then training process, how and which method we approach to build the entire model, and result and conclusion to compare our model's efficiency than others models. Moving to the next slide. So overview and related work. So before discussing the entire thing, we should know what is MLLM. The full meaning of LLM is a multimodal large language model. What is MLLM? A multimodal large language model is a type of a model that can leverage both textual and visual input data. We can simply say that this kind of model can deal with both text data and image data at the same time, or if we expect any output image from any text data or any text output from any image data, we can use this TinyGPT-V model. So in that case, the application includes for TinyGPT-V are visual content analysis. For example, if we submit any pie chart or bar chart of any particular data, this model will analyze the entire pie chart and bar chart. Based on that, it will provide the efficient data from that pie chart and bar chart that contains valuable insights for any particular data. Then it comes a visual question answering. If we provide any question or any pattern or any kind of mystery through any image data or any image, it will deeply analysis, and based on that, it will successfully provide the meaning of that image or any. It will solve that mystery as efficient as possible. Then it comes image captioning, which is one of the trending things in current AI industry. It will analyze the overall scene of any image, or if we upload any image, it will analyze every portion or every element of that image, and based on that, it will make caption or it will describe what is happening in that image. And image test transcription. If we alter any kind of image based on our demand and need, we can just simply prompt through our text, and it will alter the image. And it also goes vice versa. If we want to get any image prompt or what is containing the in this image, we can simply upload the entire image, and it will provide the transcripting thing or the what entire image is containing. Moving to the next topic, new application and inputs data type modalities are continuously being discovered. This model can also be used to from music to text generation and music to image generation. But currently we don't have enough data or enough info about that, and the entire process is still in the research observation. Moving to the next topic and over to
So that we have looked about multimodal large language models and understood about their applications. Let's now understand the background. So in this particular context, let's understand the limitations and backdrops of our existing MLLMs. The most powerful being the GPT-4. And the problem with this, or the backdrop with GPT-4, is that it has restricted usage policies, as it is not open sourced by the developers for independent uses. On the other hand, we have open source multimodal large language models such as Lava and Flamingo and Mini GPT-4. But the constraint with this is that they consume lot of a lot amount of computation resources, both for training and inference. As mentioned here, the GPT-4 uses the Mini GPT-4 uses eight Tesla A100s for both training and inference stages. Next slide, please. Now let's have an overview about our TinyGPT-V. So on the right hand side, we can see a chart where we can see the number of parameters on the x-axis, and on the y-axis we can analyze the performance of all the open source multimodal large language models. And TinyGPT-V being 2.8 billion parameters, uh, it it outperforms most of the l- large language models here. And along with that, it only requires about 24 gigs of GPU virtual RAM for training, and 8 gigs of GPU or CPU for inference. So just to give a comparison, the OpenAI's GPT-4 has an estimated 1.7 trillion parameters. Now let's understand the model architecture.
Now I will go over a high-level overview of TinyGPT's model architecture. So the general pattern that TinyGPT follows is taken from Blip 2, and it's a general strategy that's leveraging off-the-shelf frozen pre-trained visual encoders and large language models. The two main components, off-the-shelf, pre-trained and frozen. And when I say frozen, I mean that the weights are not updated during the training process. So I kind of like to think of, the overall model as sort of being like a turbocharged transfer learning situation. So the first component is the visual encoder. And what a visual encoder, it's accepting a raw image as an input, and it's transforming it into a format that the model can understand. It's essentially the image-based analog to a word embedding or the embedding layer in an LLM, for example, that's sort of encoding the quote unquote meaning of the input into a format that the model can understand. This format will likely be a vector of real numbers. And the visual encoder that is used is EVA. So it's a pre-trained vanilla vision transformer that's been pre-trained on a specific data set. And then it can extract visual features, and it can capture long-range spatial dependencies between image elements. And it can capture these long-range spatial dependencies because it is a vision transformer, and it is based on the transformer architecture. The next piece that's also from Blip 2, the general strategy, is the Q-former, the querying transformer. That's essentially filtering output from the visual encoder to produce a fixed number of output features, and it does this by leveraging these quote-unquote learned queries. So like, you know, the kind of the image embedding of the word embedding is producing kind of an abstract representation of the meaning of a word or a sequence of words or an image. These learned queries are essentially a representation of common questions that are used to perform common tasks involving image text pairs. And this component is also frozen, and it's helping the model focus on the most relevant parts of the image. Next, we have the linear projection layers, and one of them is pre-trained from the mini GPT-4 model. The other ones are randomly initialized layers. A linear projection layer is this kind of the standard, fully connected layer that you'll find in any artificial neural network. And the main purpose of these layers are to align the size, so the dimensionality of the output of the Q-former with the desired input size of the LLM's embedding layer, so that these weights can be merged. And the LLM is, so again, it's the large language model. And it's leveraging an input text prompt to generate a realistic and relevant response. And the large language models are also built off of the transformer architecture that's leveraging various attention mechanisms in order to capture the long range dependencies within the input data. So in this case, within the input text sequences. So in our case, TinyGPT is using Phi 2, and it's Microsoft's open source LLM. That's actually kind of a fun fact. It's pre-trained on synthetic data generated from GPT 3.5, which is OpenAI's model. And despite its small size, it can actually match or exceed the performance of LLMs that are up to 25 times larger. And the final piece of each training stage are the normalization and the LoRA, the low rank adaptation matrix layers. The normalization layers are necessary in order to kind of stabilize the training process and guard against common pitfalls that you might find when training a neural network. For example, dealing with the vanishing gradient problem during backpropagation. And then the low rank adaptation matrices are a set of parameters that can essentially fine tune the frozen pre-trained weights in the large language model in a memory efficient way. And again, we want it to be memory efficient because that's kind of the whole reason that the TinyGPT model is existing in the first place. Thank you.
Next, we'll go through the training process. So TinyGPT-V has 4 training stages. The vision transformer, the Q-former, and phi2 are kept frozen, while the projection and normalization layers are trained during the entire training process. The first stage is the warm-up stage. In this stage, the model is taught vision language understanding using image text pair dataset. This process involves 20,000 training steps covering about 5 million image text pairs. The second stage is the pre-training stage. While the projection layers keep on training, the model is further refined to process image modality inputs effectively. The same dataset from the first stage is used for training the LoRa module. The third stage is termed as human-like learning. Here, the model is fine-tuned using a selection of image text pairs from MiniGPT-4 or Lava. The model is given an image with an instruction, like take a look at this image and describe what you notice. The aim for this is to improve the model's ability to generate more natural sounding responses. The last stage is called the multitask learning. In this stage, the focus is on improving the conversational ability of the model as a chatbot, and the model is tuned with more multimodal instruction dataset. Next slide, please. The following are the datasets used during the entire training process. The first and the second stage utilizes the same dataset, which is a combination of conceptual caption, SBU, and Lion. In the third stage, we use the image text pairings from MiniGPT-4. The next two are the datasets used for referring expression comprehension and visual question answering datasets. The Lava dataset is utilized for multimodal instruction tuning. Flickr 30K dataset is used to improve image caption generation and object passing capabilities. And the last language dataset, which contains unnatural instruction, is used to recover the language generation ability of the model.
Yeah, so on the results and conclusion sections, there is a significant thing we can observe from the particular table given on the left side, that TinyGPT-V only comprises of 2.8 billion parameters as opposed to the particular models like Flamingo having 9 billion parameters, going up to 13 billion parameters with the models such as MiniGPT-4 and InstructBlip. And this particular models are being evaluated on 5 particular data sets. First being GQA, which is a data set for real world visual reasoning and compositional question answering. Then we have a visual spatial reasoning, which is a collection of text image pairs in English describing the spatial relationship between the caption and the text. Then we have icon question and answering, which is a data set having questions aimed at challenging the visual understanding and reasoning in the context of icon images, which is having 3 subtasks: multi-image choice, multi-text choice, and fill in the blank. Then we have Viz, which is a collection of queries, each derived from a photo taken by a visually impaired person using a smartphone, accompanied by a vocalized question regarding the image and supplemented with 10 answers sourced from a crowd for each query. Then we have the hateful memes, which is developed by the Facebook, which is specifically designed for the detection of hateful content content in memes, combining both image and text elements. So from the evaluation itself, we can see that TinyGPT-4 is beating many of its counterparts, but it was specifically observed that TinyGPT-V was passing with flying colors in the smaller data set, specialized in niche areas as compared to other its counterparts. But there is a exception, being instruct blip, where the instruct blip is working on large data sets, but still having a reasonable performance, a greater performance than the TinyGPT-5. Next, we have the pros and cons section. As we know that the TinyGPT-5 is having 2.8 billion parameters, so it is trainable locally on our commonplace hardware setups. And it is also having better performance compared to the other models which are having large parameters, as we observed in the last slide. The cons is that it is having a complex and laborious four-stage training process. As the data set size increases, we have observed that the particular performance of the model diminishes rapidly. And these are the particular links to the paper given by the author, and the GitHub repository and the Hugging Face link. Thank you, everyone.